Did you know that understanding the integral of cosine x is crucial for analyzing everything from sound waves to alternating current? The key to understanding these phenomena lies in this fundamental formula. The integral of cosine x equals sine x plus c. But what exactly is integration? Integration is the reverse process of differentiation. While differentiation finds the rate of change, integration finds the original function from its rate of change. In our case, we know that the derivative of sine x is cosine x. So by the reverse process, the integral of cosine x must be sine x plus a constant of integration. Throughout this video, we'll explore exactly where this formula comes from, work through practical examples, and see how to apply it to solve real problems. By the end, you'll have complete mastery of integrating cosine functions. Ready to master the integral of cosine? The journey starts with understanding the fundamental relationship between derivatives and integrals. The key to understanding why the integral of cosine x equals sine x plus c lies in a fundamental relationship in calculus. Integration and differentiation are inverse operations, which means they undo each other. The fundamental theorem of calculus tells us that if f prime of x equals f of x, then the integral of f of x dx equals f of x plus c. This means differentiation and integration are inverse operations. Think of differentiation and integration as opposite processes. Differentiation takes you from a function to its rate of change, while integration takes you from a rate of change back to the original function. Here's the crucial relationship we need. The derivative of sine x with respect to x equals cosine x. This is a fundamental trigonometric derivative that you should memorize. Now we can apply the fundamental theorem of calculus. Since the derivative of sine x equals cosine x, then by the inverse relationship, the integral of cosine x dx must equal sine x plus c. This arrow represents the inverse operation. We're essentially working backwards from the derivative relationship to find the integral. The constant c appears because when we differentiate, any constant term disappears. So we must account for all possible constants when integrating. Remember this key concept: integration undoes differentiation. This fundamental relationship is what allows us to find integrals by recognizing derivative patterns. In our next section, we'll walk through the complete step-by-step derivation of this integral. Now we'll derive the integral of cosine x step by step. Our goal is to show that the integral of cosine x equals sine x plus c. Step 1, we need to recognize the fundamental relationship between sine and cosine. Remember that the derivative of sine x equals cosine x. Step 2, by the fundamental theorem of calculus, if the derivative of sine x is cosine x, then the antiderivative of cosine x must be sine x. Step 3, we must add the constant of integration c. This is crucial because when we differentiate any constant, we get 0. So there could be any constant added to our antiderivative. Let's verify our result by differentiating sine x plus c. The derivative of sine x is cosine x, and the derivative of the constant c is 0, giving us cosine x. This confirms our integration is correct. Perfect. We have successfully derived that the integral of cosine x equals sine x plus c. This three-step process shows the logical connection between derivatives and integrals through the fundamental theorem of calculus. Now that we understand the derivation, we're ready to apply this formula to solve actual integration problems. Now we'll work through our first example to see how to apply the integration formula for cosine. This is a straightforward problem that demonstrates the direct application of what we've learned. The problem asks us to evaluate the integral of cosine x with respect to x. This is exactly the type of integral we've been discussing, so we can apply our formula directly. We apply the integration formula directly. The integral of cosine x equals sine x plus the constant of integration c. This is our complete answer. Notice that we must include the constant c. This constant is absolutely essential because indefinite integrals represent an entire family of functions, not just a single function. Every antiderivative of cosine x differs by a constant. To better understand what this constant c means, let's visualize this family of antiderivatives graphically. We'll see how different values of c create different curves. Here we see the coordinate system where we'll plot our family of antiderivatives. Each curve represents sine x plus a different constant value. Watch as we draw multiple curves, each representing sine x plus a different constant c. Notice how all curves have the same shape. They're just shifted vertically by the constant amount. This is the key insight. All these curves are antiderivatives of cosine x because they all have the same derivative. When you differentiate any of these curves, you get cosine x. The constant c simply shifts the entire curve up or down without changing its shape or slope. This completes our first example. We've seen how to directly apply the integration formula and understand why the constant of integration is essential. The integral of cosine x is sine x plus c, representing this entire family of antiderivative functions. Now we'll work through a definite integral example that has a beautiful geometric interpretation. We want to find the area under the cosine curve from x equals 0 to x equals pi over 2. First, let's visualize this problem. Here's the graph of y equals cosine x. We want to find the area of the shaded region from x equals 0 to x equals pi over 2. Step 1, we set up the definite integral. The area under the curve equals the integral from 0 to pi over 2 of cosine x dx. Notice how the bounds of integration match our shaded region. Step 2, we apply the antiderivative. Since the antiderivative of cosine x is sine x, we get sine x evaluated from 0 to pi over 2. This bracket notation means we'll substitute our bounds next. Step 3, we evaluate at the bounds using the fundamental theorem of calculus. This means we substitute pi over 2 into sine x, then subtract sine of 0. Step 4, we calculate the trigonometric values. Sine of pi over 2 equals 1 and sine of 0 equals 0. So we get 1 minus 0, which equals 1. Therefore, the area under the cosine curve from 0 to pi over 2 is exactly 1 square unit. This beautiful result shows how definite integrals give us precise geometric measurements. Notice how the shaded region represents exactly 1 unit of area. This example demonstrates the power of definite integrals. We transformed a geometric question about area into an algebraic calculation, showing that mathematics provides exact answers to real-world problems. Now we tackle a more challenging integral that involves the chain rule. We'll evaluate the integral of cosine of 2x plus 3. Here's our problem. Find the integral of cosine of the quantity 2x plus 3 with respect to x. We can use the general formula for integrating cosine of ax plus b. The integral equals 1 over a times sine of ax plus b plus the constant of integration. First, we identify our values. Comparing 2x plus 3 with ax plus b, we see that a equals 2 and b equals 3. Now let's apply the formula step by step. Step 1, we substitute our values into the formula. Since a equals 2, we get 1/2 times sine of 2x plus 3 plus c. But why do we need the factor 1 over a? This comes from the chain rule. When we differentiate 1/2 sine of 2x plus 3, we get 1/2 times cosine of 2x plus 3 times the derivative of the inside, which is 2. The 1/2 and 2 cancel out, giving us exactly cosine of 2x plus 3. Let's verify our answer by taking the derivative. Step 2, verification. We take the derivative of our answer, 1/2 sine of 2x plus 3 plus c. Using the chain rule, this equals 1/2 times cosine of 2x plus 3 times 2 plus 0 from the constant. Simplifying, we get cosine of 2x plus 3, which matches our original integrand perfectly. Our answer is correct. Therefore, the integral of cosine of 2x plus 3 equals 1/2 sine of 2x plus 3 plus c. Remember, the key insight is that the factor 1 over compensates for the chain rule when differentiating. Now that we've covered the basics of integrating cosine, let's address the most common mistakes students make. Research shows that 34% of students initially confuse signs in trigonometric integration, so you're definitely not alone if you've made these errors. The first and most common mistake is forgetting the constant of integration. When we write the integral of cosine x dx equals sine x, we're missing something crucial. The correct answer must include plus c, because there are infinitely many antiderivatives that differ by a constant. The second major mistake is sign confusion. Some students incorrectly think the integral of cosine x is negative sine x plus c. This is wrong. The correct answer is positive sine x plus c. You might be confusing this with the integral of sine x, which does give negative cosine x plus c. The third common mistake involves the chain rule. When integrating cosine of 2x, students often forget to account for the coefficient. The wrong answer is sine of 2x plus c. The correct answer requires dividing by the coefficient of x, giving us 1/2 sine of 2x plus c. Here are 3 essential tips to avoid these mistakes. First, always include plus c for indefinite integrals. Second, double-check your work by differentiating your answer. It should give you back the original function. Third, pay careful attention to coefficients inside trigonometric functions. For example, if we claim the integral of cosine x is sine x plus c, we can verify this by differentiating sine x plus c, which gives us cosine x. This confirms our answer is correct. Remember, making mistakes is part of learning. The key is recognizing these common patterns and developing good habits, like always including the constant of integration and verifying your answers through differentiation. Now that we've mastered the integral of cosine, let's see how this fundamental formula appears in 3 important real-world applications that you'll encounter in physics and engineering. First, simple harmonic motion. When a pendulum swings or a spring oscillates, the velocity follows a cosine pattern. By integrating this velocity function, we can find the position. The velocity of a pendulum is given by v of t equals negative omega sine of omega t. To find position, we integrate this velocity function. Integrating the velocity gives us the position function. The integral of negative sine becomes positive cosine, giving us x of t equals cosine of omega t plus c. Second application, AC circuit analysis. In electrical engineering, alternating current voltage often follows a cosine pattern. When we need to find the charge, we integrate the current function. If the current is I of t equals I naught cosine of omega t, then to find the total charge, we integrate this current function. The integral of cosine gives us sine, so the charge function becomes q of t equals I naught over omega sine of omega t plus c. Third application, wave mechanics. Sound waves, light waves, and many other wave phenomena involve cosine functions. Integration helps us analyze wave properties like displacement and energy. For a wave with acceleration, a of t equals negative omega squared cosine of omega t, we can integrate twice to find velocity and then displacement. Integrating once gives velocity, and integrating again gives displacement. Each integration of cosine produces sine, building our complete wave solution. Now let's recap everything we've learned about the integral of cosine and why it's so important in mathematics and science. The fundamental formula we've learned is the integral of cosine x dx equals sine x plus c. This simple relationship connects trigonometric functions through calculus. Remember these 3 crucial points. First, the constant of integration c is essential for indefinite integrals. Second, this formula works for any cosine function with proper chain rule adjustments. Third, it appears everywhere in physics and engineering. Whether you're analyzing pendulum motion, designing electrical circuits, or studying wave behavior, the integral of cosine gives you the mathematical tools to solve real problems. If this video helped you understand the integral of cosine, please give it a thumbs up and subscribe for more calculus tutorials. What integration topic would you like to see next? Let me know in the comments below. Next up, try tackling more advanced integration techniques like integration by parts or trigonometric substitution. Keep practicing and you'll master calculus step by step.